Yes, so thanks a lot for having me. And what I want to do at this last talk today is bring you a little bit back to the world of magnetism. And we'll see how we can drive a special type of magnetic systems, and we'll be motivated by the physics of Archimedean screws. But maybe I should first mention the work I'm presenting is really the work of Nina Delcer and Lukas Heinen. So let's start. So the question from which I want to start is whether we can just build some small machines using driven quantum matter. And I think that's one of the questions that motivates us. And I think there are two reasons for that. And the first one is maybe the most important one at the moment, namely we want to explore really physical mechanism and some fundamental concepts and have some fun. But certainly the second idea is ultimately also to create something useful from that. And what I want to start from is one of the oldest machines which we know, namely the Archimedes Crew, which was invented by Archimedes some 2,000 years ago. So he's one of the, kind of the ultimate, well, one of the first physicists, mathematician, inventor, engineer. And he invented this type of screw to train ships mainly. Good. So when we think about what is the principle behind Archimedean screw or behind actually any screw, then it's the idea that when we do rotation, then this involves translation. Yeah. So when you drill the screw in the wall, then it's about bringing the rotation to a translational mode. That's precisely what we want to use. And what we need for that is a screw. And the screw is provided by a helical phase of a chiral magnet. So just a magnet which precisely where the magnetization precisely has this screw-like shape. And from the point of symmetry, what you should think about here, that this object is invariant when you do a combination of a spin rotation and translation. So spin rotations and translations are locked, in this case by some spin orbit interactions. And this is the operating principle which we want to use to get a screw-like scheme. Okay, now we could ask, how do we get that, and do we have materials to do that? And indeed, there are now literally hundreds of systems where you find a ferromagnetic state where you have such a helical magnetic order. And there are metals, insulators, semiconductors. You can do that at room temperature, at low temperature, and most recently, these systems have been intensively studied because they also realize often magnetic skyrmion phases. That's another very interesting type of phase, but we'll not considering this thing, but a much simpler screw-like helical structure. And in a very simple case where you get that, is to just take a cubic magnet which lacks inversion symmetry, and then you have some spin orbit interactions, and because the lack of inversion symmetry, they like to twist the magnetic structure, and therefore you naturally get such screws which pitches range from nanometer to micrometer depending on parameters. And two materials which will show up in the following also as examples are manganese silicide and carboxylene oxide, one a metal, one an insulator, but they are kind of the most famous skyrmion systems, and therefore they are very well understood. Good, so let me get a little bit more concrete. So we mainly actually work with classical equations of motion. So we have a standard ferromagnet with a bit of Dzerzhinsky-Moria interaction, which likes to twist the magnetic state to get these helical phases. There are some dipole-dipole interactions. And most importantly, we'll apply an external magnetic field, which has a static component, but most importantly, an oscillating component that will drive our non-equilibrium state. Good. So let's try to solve this problem, and we'll work in a regime where this oscillating field is always very small. And so the starting point is just good old perturbation theory. So without perturbation, we just get this helical or conical state of matter. So it's a simple screw-like magnetization, where magnetization depends only on the z direction, and you're just translation invariant in the other direction. Now we switch on the oscillating magnetic field, and first when we consider this to linear order, then we get just standard linear response theory. And in the materials which I mentioned, this has been extensively studied experimentally. So here's a typical experiment, and there you see that you can excite two modes of this helical structure. And these two modes will play also a role in the following. But let me just mention that the theory is fully under control, so we get absolute, so parameter-free descriptions of all these resonances for these helices are extremely well understood. But now the fun starts when we now go to second order, and that's also a much more unexplored regime. And so linear response happens at frequency omega. So its clear quadratic response happens at frequency 2 omega. But what will be of interest mainly to us is also at frequency 0. And why is that interesting? Because at frequency 0, our system has a Goldstone mode. And what we can now hope is that we pump into the Goldstone mode of our in the Goldstone mode of our system. That's precisely what this screw-like motion will be. And quite generically, you can expect this to happen whenever symmetries allow that. And indeed, in this system, you just take any oscillating magnetic field, and you can expect to get some pumping in this zero frequency mode. So while I'm considering a specific system here, a very similar story can be told for many, many systems with Goldstone modes. Okay, so let me go on. Now let's just do a little bit of calculation. It turns out that one can, in this case, calculate almost everything analytically, at least to linear order. You can just get the full analytic solution, and just to show that one can even treat the case with dipole interactions. I show you here just a formula for the resonance frequency in this system, just to prove that one can do these calculations just analytically. Now, fun starts, however, at quadratic order, and please don't look at these equations. But what I want to emphasize is when you just take these equations, Fourier transform them, and try to find a solution, then you find out that there is simply no solution at zero frequency and zero momentum. So what's going on? And how is this resolved? And what's going on is that we pump into this Goldstone mode, and therefore we switch on this screw-like motion. So when we make this ansatz, that the angle of our magnetic structure changes linearly in time, so makes this screw-like motion, then we can easily solve these equations. So messages. To second order in perturbation theory, we unavoidably get this thing moving, and we induce our screw-like motion. And I'm not sure how well this movie transmits to via Zoom, but what you should see is that we have some rapid oscillations that come from the external magnetic fields, but this triggers now a much slower rotation of the whole screw. And what is shown here is the frequency of this screw as function of driving frequencies, really calculated for one specific materials where we understand everything very well. And you see by tuning the driving frequencies, one can, for example, switch between a screw going in one direction and going in the other direction. And maybe I should also emphasize here that we can do numerical simulations and analytical treatment, and you get perfect agreement between those as you expect, because that's just a perturbative effect arising naturally to second order perturbation theory. Good. So we've reached our first goal. We found such an Archimedean screw solution. Now we have to think a little bit whether this state is really stable. And let me start by looking a little bit of analytics. So that just tracks the angle of a single spin for different strength of the oscillating magnetic field. So we start with 0.5 millitesla, and there you just see some oscillation and a linear growth. So this is just our Archimedean screw solution, which we calculate now analytic numerically, everything. But then you increase the amplitude, and there you see that suddenly an extra period in time shows up, so that so we get some type of time crystal which forms, and when we increase things even more, then we enter a chaotic regime. Now that's numerics, but it turns out this numerics depends super strong on system size and how you do the numerics. So actually, we were not able to understand that before we did an analytic treatment of these instabilities. So let's look at the stability of the Archimedes screw. And what we should do is what we are just doing is a standard stability analysis. So we just do spin wave theory for this spherically driven system. And what I start showing you is the spin wave spectrum, so the Fouquet spin wave spectrum of the unperturbed system. So no oscillating field gets switched on. And what you see here is there's a crossing. There are crossings of curves, and these crossings actually, or this crossing I'm pointing to, that describes something which is completely unavoidable in the system. Namely, there's a resonant process where I can create a pair of Magnons. And whenever you have a resonant pair creation possible, then you can expect that something is happening. And here's the corresponding calculation in the presence of a oscillating magnetic field. And what you see, what you should look at is mainly the lower plot. And if the amplitude of the drive is sufficiently strong, then what you get here is negative decay rates. So the system develops an exponentially growing instability. Good, so that's what you can do analytically, but what you don't see is what that means physically. And physically, it means indeed that we have a time crystal forming. Namely, we get an excitation which oscillates with the momentum defined by this crossing, and with the energy defined by this crossing, we get a new oscillation mode. Oops, sorry. It was once too fast. Let me try to start this again. So when we now increase the driving amplitude, we start from this screw-like motion, so where the frequency of screwing just grows quadratically with a magnetic field. Then precisely at the point where theory predicts it, we get an instability to a time quasicrystal, so where these extra frequencies show up, and ultimately a regime of chaos. And this regime is actually, the numerics is not really reliable, and we can't say too much about that. But the other regimes are well under control. Good, and here's again the same thing in a different way to view it. So here we track an angle as function of time. Small amplitudes, we get a regular screw. Larger amplitudes, the time crystal, and finally we enter a chaotic regime. Good, and let me emphasize that the properties I'm discussing here is really a very generic property of such magnetic systems driven by oscillating magnetic fields. Namely, if we have some incommensurate magnetic order, we have a corresponding Goldstone mode. And if it's symmetry allowed, then we can expect that this translational Goldstone mode is activated. And at least in the absence of pinning, that will happen for arbitrary weak drive. And the strength of this activation of this Goldstone mode grows like b squared. A second thing which is also unavoidable is a next to leading order instability, namely the resonant creation of Magnum pairs. And this will happen as soon as the pumping gets larger than some damping. Yeah, and the damping can come because it's a metal system and we get damping to the coupling to a metal, or it can come from Magnum-Magnum interactions. But as soon as now the pumping increases the damping, then something has to happen. And at least what we have seen here is that we get really a Magnum laser. So we get an oscillating texture which oscillates and at some momentum, at some frequency where this resonant condition is met. And finally, for stronger driving, we get the chaotic system. Now, let me come back to where we actually started, namely go back to good old Archimedes. And what we obviously want to do now, after we have our screw, we want to pump something with it. Yeah? And you can think of pumping charge, heat, and spin. And I want to focus here on a charge pump because that's the easiest one to detect experimentally. So we now think about having metal. And now we have to couple the electrons to our Archimedean screw. And we do this in the usual way. So we have an exchange coupling of the electrons to the system. But it turns out that two factors are now essential here. First, we have, importantly, to include spin-orbit interactions to get the Archimedean screw really doing some work. And second, to be semi-realistically, we should think about the effect of disorder in the system. Good, but let's first ignore disorder and let's assume that there's no disorder, no umklapp scattering, nothing, and then it's very simple. You can just go to a coordinate system co-moving with our screw. And then it's clear that in this co-moving frame, there is no current, but in the lab system, there will be a current. So we'll get a decent current in the system, actually a gigantic current if you put it in realistic parameters. But that's an unrealistic limit. What we should take into account that we have lots of disorder, or that we have some disorder in this system. And there we should better not do this transformation to the co-moving coordinate system because the disorder is moving in the other direction. So that would be bad, but we can still choose an appropriate coordinate system, namely choosing spin quantization axis parallel to the local magnetization. And then we can solve that using essentially perturbation theory and can calculate the resulting current. So what do we get? Well, so what I show here is now the current is function of some scattering, some lifetime, which parameterizes the amount of disorder in the system. And you get, roughly speaking, what you may naively expect, namely in the clean limit, we get this maximal possible current, just everything is co-moving. The current is strongly suppressed by disorder, however, when you have a dirtier system. Good, but now we can really think a little bit about experimental parameters, and we can use that some of these common systems are also pretty clean. You know? So, for example, a system like manganese silicide has mean free path, which can be larger than 1,000 angstroms without any problems. So let me, on here my final slide, let me look a little bit at numbers and how realistic that is. So the biggest enemy for our whole scenario is the pinning by disorder. And luckily, we know quite a bit about quantitatively what pinning is doing because we have studied before in the same system how skyrmions are pinned and depinned. So what we can say for sure is from our estimates that we are way above the pinning thresholds. So we should get this thing really moving. And finally, we can ask what types of currents do we expect. And if you plug in the numbers, then you get gigantic current densities even in this dirty limit. And so it should be very easy to detect that. And with that, I want to close. So I gave you an example of a simple machine, and hopefully soon also in experimental talk. And it builds on a very general principle, namely the pumping of Goldstone modes. And we got as a bonus, we got some interesting physics like formation of time quasicrystals, and I think it should be very nice systems also for future experiments. Thank you.